In this presentation, we will see how to design 3-bit up-down synchronous counter. We have already designed the asynchronous version of this counter, and in that case, the clock was not simultaneous. The clock was not given at the same time to all the flip-flops used. But here we are going to give the same clock at the same time to all the flip-flops. The flip-flops I have used are ABC, 3 flip-flops, because we have to design 3-bit counter. This is known to everyone. If you are in this presentation, I hope you have learned the basic of the counter. And TC, TB, TA are the input of the 3 flip-flops that we are going to use. QC, QB, QA are the output of the 3 flip-flops, and definitely they are the output of our 3-bit counter. We have the same logic as compared to the asynchronous one. We will have a control mode or a control input that we call as M, and depending upon its value, either we will count upward or downward. And in this case, I have assumed that when M is 0, when M is low, we will have up counting, and if M is 1 or high, we will have down counting. So depending upon this thing, we have to design it, and definitely there is a change, and the change is in the design. The logic is same, but the design is different as compared to the asynchronous one. So let's start it without wasting any time. First of all, I will explain the state diagram for this. We have 8 states because you already know 3-bit asynchronous counter or 3-bit synchronous counter will have 8 states, because 2 to the power 3 will give us 8. And if I talk about the maximum count, then it will be 8 minus 1, that is 7, and 7 is represented by 1 1 1. 0 0 0 is the initial state, and we will start our counting from this state. And if I talk about this first 8 cases, when M is 0, we will have the up counting. So let's see how it looks. We will start from 0 0 0, we will go on 0 0 1, then we will go on 0 1 0, that is our 2, then 3 4 5 6 7. This is up counting. Why it is up counting? Because for every passing clock pulse, we have a value that is greater. We were on 0, and once the clock pulse is passed, or we have the change in the circuit, the flip-flops are in the operational state and they have generated the output, we have the value equal to 001. This QC, QB, QA is changed to 001 from 000. So we have a higher value. In the same way, for the next clock pulse, we have 010, that is 2. So we have the higher values for every passing clock pulse. So we call it up counting. And in the same way, if I talk about the down counting, the value of M, that is our control input, is 1, and we have the 8 possible cases. So let's see what is there in case of down counting. You can see I have started from 1 1 1, that is 7, the maximum count, and for the passing clock pulse I am on 6. So we have a lower value for the passing clock pulse. Then I will be on 5 4 3 2 1 and back to 0, and then back to 7. So this is what we have to do in down counting, and we have to implement this logic by using the T flip-flops. That's all we have to do in this presentation. So let me write this important point down. This particular case, brown one, is when M is equal to 0, and this green one is when M is equal to 1. So what I can say when M is equal to 0, we have up counter, and when M is equal to 1, we have down counter. So let's design our circuit. I have already made this table. Only thing we have to do is to find out the next states and the input to the flip-flops. And once we are having this, we will implement it by using the 16 cell K-map, and then the final step is the implementation of the circuit. So we will do this quickly, and let me write these things down first. This one is my control input. This QC, QB, QA is definitely the present states. QC plus, QB plus, QA plus is the next states, and this TC, TB, TA is the input of flip-flops. So let's start with it. We will first find out the next state of the first 8 cases, that is for the up counting, because M is equal to 0, the reason for the up counting. So I will write up counting for the first 8 cases. Up counting, and we will use this state diagram to find out the next state. If we are on 0 0 0, you can see the next state is 0 0 1. So the next state is 0 0 1, and I have already told you it's very simple to write down the next state in case of counter, because every time you have to increment to 1. That is the counting actually. So the present state is 0 0 1, the next state is going to be 2. So it is 0 1 0. In the same way, if present state is 2, the next state is 3 0 1 1. You can also compare it from this state diagram. The present state is 2, the next state is 3, and we are talking about the up counting, so you have to consider these brown arrows, not the green one. And when the present state is 3, the next state is 4 1 0 0. In the same way, 5 6 7, and again back to 0. So we have completed the next state column for the up counting, and I will use the excitation table for the T flip-flop to get our input TC, TB and TA. I hope you remember the excitation table of the T flip-flop, because we have used it a lot. We have done lots of practice of this thing, so there is no need to make another extra excitation table for T flip-flop. We can do it directly. When T is 0, we have memory, and when T is 1, we have toggling, and the excitation table will give us the value of T depending upon the value of the present state and the next state. So first we will find out TC, and as I'm talking about TC, C is the subscript. It means we are talking about the C flip-flop, and we have to see QC and QC plus, because they are the present state and the next state for the C flip-flop. So 0 is the present state and 0 is the next state. It means we have memory, and memory is there when T is equal to 0. In the same way, we will complete the 8 cases. 0 is the present state, 0 is the next state. It means again T is 0. 0 is the present, 0 is the next. So T is 0. 0 is the present state, next state is 1. So definitely there is toggling, and when there is toggling, we have T equal to 1. 1 1 again same state. So 0 1 1 again same state. 1 1 again same, 1 0 toggling, so we have 1 as the value of TC. In the same way we will do for the TB, that is the input of the B flip-flop, and for this we will consider QB as the present state and QB plus as the next state. So let's do it. 0 0, it means TB is 0. 0 1, toggling is there, so 1 1 1 memory, so 0 1 0, so 1 because of toggling. 0 0 0 0 1 1 1 1 will give us 0, and finally 1 0 will give us 1. So this is how TB is there for the up counting, and in the same way we will do for TA. TA will be determined by using QA and QA plus. 0 1 toggling is there, so 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0. So in all the 8 cases we will have toggling. So let's write it down. For toggling we have TA equal to 1. Okay, so we are done with the up counting case. Now we will move to the next part of this table, that is for down counting, and for down counting we will have the control input equal to 1 or high, and we again have to follow the same steps to find out the next state. We will use this state diagram, or you can directly write it down, because you know what will happen in case of down counting. Instead of incrementing 1, we will decrement 1. So 0 0 0 is there, it means the next state is 1 1 1. 0 0 1 is there, it means the next state is 0 0 0. 0 1 0 is the present state, so next state is 0 0 1 0 0 1. In the same way 0 1 0 0 1 1 1 0 0 1 0 1, and finally 1 1 0. So this is how the next state looks for the down counting, and we have to follow the same steps again to find out TC, TB and TA for the down counting. We will use the excitation table for T flip-flop. I will write it down directly. TC is 1 0 0 0 0 0 0 1 0 0 0, and for TB I have 1 0 1 0 1 0 1 0. You can easily find out these values by using the excitation table. I'm not going to do it again, you can do it by yourself. And for TA we will have toggling for all these 8 cases, so it is high. And in this way we have completed the table, the circuit excitation table for 3-bit up down synchronous counter. And this part is for down counting. And now the next step is to find out the minimized expression for TC, TB and TA, and we are going to use the K map for that. And as there are 4 variables, you can see there are 4 variables M, QC, QB and QA, we have to use a 16 cell K map. I have already made one. I will paste it and we will use it directly. And we have to use 3 such maps for TC, TB and TA. So I will paste two more maps we require. Okay, and this is the last one. Okay, first I will find out the value for TC. So this first map is for TC, and we will fill it by this table. Initially we have 0 0 0 1, so we have 0 0 0 1, then we have 0 0 0 1 again, so 0 0 0 1, and for the last 8 values I have 1 0 0 0, so 1 0 0 0, and again we have 1 0 0 0, so 1 0 0 0. We have filled the K map, and it's time to make the pairs or group of 1, you can say. In this case we have pair, and these are the 2 groups that I can see, and TC is equal to, let's say this group is 1, the group of 1 we call as implicants, and this group of 1 is 2, so TC is equal to 1 or 2. You can easily find out the value for 1 and the value for 2. I can write TC equal to, for the first group I can write M complement QB QA, or for the second group I have M QB complement QA complement. In the same way I will use this map to find out the value for TB, and for the first 4 cases I have 0 1 0 1, so we have 0 1 0 1, and for the next 4 cases I again have 0 1 0 1, then we have 1 0 1 0, so 1 0 1 0, and after this we have 1 0 1 0. So let's make the group of ones. This is my first group, this is my first group, and this one, the group of 4 ones, is my second group. So TB is simply M complement QA or MQA, that is definitely equal to M XOR QA. Now we will do for TA. That is very simple, because you can see it is 1 or high every time. For all the 16 cases it is high, so we are going to get 1 as the value for TA. All the cells will have 1, and I can make the group of 16 ones, and we have a 16 cell K map, so definitely TA is equal to 1. We are done with our K maps, and now we will try to implement it. So we require 3 T flip-flops. So let me copy the first flip-flop. This is A, and in the same way we need the B flip-flop. I'm making some space between these 2 flip-flops because we have to implement the logic, and this one is the last flip-flop that we require, which is C flip-flop. Let's write down the input, and also we have to give a common clock to these 3 flip-flops. That's why we are calling it synchronous counters. This is the clock, and it is given to the 3 flip-flops at the same time. Okay, this one is the clock, and this is A flip-flop, this is B flip-flop, this one is C flip-flop. This is TA, TB, TC, The output is QA, QB, QC, and the QA complement is there. I'm going to use QA complement, that's why I'm writing it down. QB complement and QC complement. Now let's see what logic we have from the K-map. TA is equal to 1, so I will give TA logic 1 with no problem. And before implementing this logics, let me make the control input first. The control input is M, and it will go like this. I will use a NOT gate to have M complement, because you can see we have M complement in our expression from the K-map. So this is the control input, and if I want to implement TB, we have M complement and QA, so a 2 input AND gate is required, or M and QA. So we need AND gate here, another AND gate here, this one, and then a OR gate. This is my OR gate. Let's see what we have to do now. M complement QA. So I will have M complement from here. This is the first input and QA is the second input, and the output of this AND gate will definitely go to the OR gate, and the second min term is MQA. Actually this is QA complement, that's why we have M XOR QA, a small mistake. So QA will go, and we need M, so M is given as the second input, and then we will give the output to the OR gate, and the output of the OR gate will be given to TB, because it is nothing but equal to TB. So you can see how we have to implement it, and now we will try to implement TC. TC is equal to M complement QB QA. If I rearrange this little bit, I have M complement QA QB or M QA complement QB complement. You can see this M complement QA is nothing but the output of this AND gate. Here I'm having M complement QA, and this M QA complement is the output of this AND gate, M QA complement. So what I can do, I will take this output and give it to the AND gate, so that the output of this AND gate is nothing but M complement QA from here, you can see, and this is QB, so this is QB. In this way we have the first min term for TC, and we'll try to implement the second min term in the same way. I will take the output of this AND gate and give it to this 2 input AND gate. We need another OR gate, okay, and then we'll give it to TC. So you can see we have a up down counter that is definitely 3-bit up down counter, and it is synchronous because the clock is given simultaneously, and we have to take just QA from here, take QA, QB and QC. Now there is one question, what if I want to have a 4-bit synchronous up down counter? Actually there is no need of another lecture for this topic. I'm just going to cover it in this only. You have to just take this like we took this one, and then this in again give it to the AND gate like this, use a AND gate, okay, and then again use a OR gate, and the output of this OR gate will go to TD. So we have a 4-bit synchronous up down counter. And what if you want to use JK flip flop? Then only a small change you need to do. You don't have the T as input, but you have JA and KA as the input. This one is JA and KA. We will have JB, KB. So this logic 1 will be given to K as well, and the output of this OR gate is not only for JB, it will also go to KB. Similarly, this output will go to KC also along with JC. So these are the 2 small changes that you can do to have a 4-bit synchronous up down counter, or you want to implement with the JK flip flop.